Okay, hello everyone. Here is the first problem. We have this frictionless slide that looks like this. The first part here is supposed to be a straight line, but then it becomes it's part of the sector of a circle at the end here, or a cylinder. Here the radiuses are, and this angle, both of these angles are theta. And so this height is h. And first we drop a small object of mass m from rest at the upper end and let it slide down. And then we want to find the maximum height x of its trajectory above the lowest point after m leaves the slide. So then it goes here, and we want to find this x. Okay, so first we can see that we can find the velocity of the mass at the end of the slide pretty easily. That's just conservation of energy. And from that, we get that mgh is equal to 1/2 mv squared plus mg times this, the height here. And that would be mg times r, and then 1 minus cosine theta. So now we can easily solve for v. This means that v is just equal to 2g times h minus r, 1 minus cosine theta, and all that square root. And so, okay, so actually we didn't actually need to find v because the next part also, our next step also relies on conservation of energy. So we really only need v squared, but that doesn't really matter now, because we use conservation of energy again to find the height x. But the important part is that we only take the vertical component. Since there's no force on the horizontal component, it doesn't factor in when we're using conservation of energy. So then the vertical component is just this v times sine theta. So then the energy would be 1/2 m v sine theta squared plus the height here, which again is mg r, 1 minus cosine theta, and this has to be equal to its maximum height, which is mgx. Okay, so then this means that okay, so that we can first cancel out all the m's, and so then this 1/2 times v sine theta squared, that would be 1/2 times 2g h minus r, 1 minus cosine theta, then times sine squared theta plus r is 1 minus cosine theta is g times r is equal to gx, and we can cancel out the g now, and so then we get that this would be x is equal to at h minus r times 1 minus cosine theta times sine squared theta plus r times 1 minus cosine theta. This entire thing would be h here. So then now we can simplify this further. This first part, this would be h times sine squared theta. Then I believe that one would be plus r 1 minus cosine theta times 1 minus sine squared theta, when this 1 minus sine squared theta is of course just equal to cosine squared theta. So then this would be h times sine squared theta plus r cosine squared theta minus r cosine cubed theta. And so that is the answer to the first problem. Does anyone have any questions? Okay, since it appears no one has any questions, then I'll move on to the second problem now. You have some students measuring the acceleration of gravity using a simple pendulum. And so they find that the length is L, which is some number with an uncertainty, and then they find the period is something else. And all uncertainties are Gaussian, and then we want to find, and then so it asks us how we should record the acceleration of gravity that we would compute, including the uncertainty. So then first, what do we have? L is equal to 1 plus 1 plus 0 plus or minus 0.5 meters, and T is equal to 2 plus or minus 0.1 seconds. Okay, so now we know that for a pendulum, the period T, the relationship between T and L is T is equal to T is just equal to 2 pi times square root L over G. And so this means that, of course, T squared is equal to 4 pi squared L over G. So G is equal to 4 pi squared L over T squared. Okay, so now we want to find the uncertainty here. And so first let's look at this 1 over T squared first. If we have some function f of x, which is equal to x to the n, and then the uncertainty would be dx. So then if we take the log of this f of x, then we would get log f of x is equal to n log x. And so, and then if we take the derivative, we know that the d over df times log f would be equal to 1 over f. So basically what this means is, yeah, that d times log f is equal to df over f. So df over f is just equal to n times dx over x. That's what we get. So since before dx is the uncertainty, then this dx over x is what we call the relative uncertainty. And so this allows us to compute the relative uncertainty of this function f. And since the uncertainty, and in this case, we have 1 over T squared, it would just be 2 instead of -2 because they're basically the same anyway. So then, yeah, so then we know that this uncertainty for 1 over T squared, the uncertainty would be 2 times, then for 1 over T squared, we would have this d times the relative uncertainty of df over f is just equal to 2 times d over t. And since dt over t is 0.05, this would be equal to 0.1. Yeah. Okay, so then now we know one of the rules for this error propagation is that when we have two things multiplied together, then this, if we have like f is equal to x times y, then df over f is just equal to this. This is something like everyone should know. And of course, we can just apply it again. So then we would have since dx, in this case we would have L and T squared. And so we already figured out dt, this d of 1 over t squared over 1 over t squared, that's the relative uncertainty for that. And this is equal to 0.1 squared plus the uncertainty in L, which is 0.05 plus 0.05 squared. And then this is the relative uncertainty for the entire function g. Since there's also a 4 pi squared part, but we know that these constants don't matter. So this is about equal to like the 0.111, I think. And so then we can calculate it. This is actually an F equals ma problem, so it should be multiple choice. And then the answer it gives is 9.9 plus or minus 0.11, I believe. Yeah, no, I mean plus or minus 1.1 meters per second squared. So that is the answer, although you can get some different measurements too. But basically, just calculated the relative uncertainty here. And since G isn't that hard to calculate, then you can just figure it out. Does anyone have any questions? Okay, since it appears that no one has any questions, then that's it. And thank you for listening.